All right, we're going to look at some of the review problems from chapter 4 through 4, 6. And we're going to start here with just question number 1. And with all of these questions, the thing to remember is figure out some sort of model, create a picture. That often will help. Figure out what equations you're going to need to use. Find the derivative of the equation you're trying to maximize or minimize. Set that equal to 0, solve it out. Okay, so we've got a piece of molding 179 centimeters long. It's going to be cut to form a rectangular picture frame. What dimensions will enclose the largest area? So what we're dealing with here is a rectangle shape. Something like this. And I like to label this as X and Y because X usually runs left and right, Y usually runs up and down. It's give it easier for me to see. And from this, I'm cutting this molding of 179 centimeters into a rectangular picture frame. That's perimeter. They have just given us perimeter. So we know that 2x plus 2y is perimeter, and we know that that's going to equal 179. Okay. Then we want to know what dimensions of this will give us the largest area. Area then of a rectangle is x times y, which we don't have any information for the area other than we know x times y. That's it. So what we're going to do, let's start with that 2x plus 2y equals 179, and let's just solve for one variable. You could solve for any variable you want to. I chose to solve for y. Generally, we're used to seeing equations say y equals. So in that case, just out of habit, so 2y is equal to 179 minus 2x. Divide everything by 2. Y equals, and then 179 divided by 2, I got is 89.5 minus x. So there's what y is. What we can do is take that y that we're using for perimeter and substitute it in for this y right here, because the equation we want to maximize, we want the largest area. So we're going to take the derivative of the area equation, and when I do that, I'm going to have a equals, now watch this, x times y. You see that? X times y. X times y. You could take derivative from here if you want to. I think it's easier to go ahead and go one more step and say 89.5x minus x squared. I think it's easier to go here. And then take the derivative of the area. A prime or dA dx. But either way, you're going to end up with 89.5 minus 2x. And we want to set that equal to 0. That will give us our maximum area. You can find maximums or minimums of any equation by finding the derivative and setting that equal to 0. So go ahead and move the 89.5 over. Negative 2x equals negative 89.5. Divide both sides by the negative 2, and you're going to get 44.75. I already punched that into my calculator. So you get xt equal 44.75. Well, believe it or not, this is going to end up being a square, because if I put 44.75 in here, 89.5 minus 44.75 is equal to 44.75. So my dimensions then are going to be 44.75 centimeters by 44.75 centimeters. And that right there is the largest area of a rectangle we can get that fits this particular set of rules. A company is constructing an open-top, square-based rectangular metal tank that will have a volume of 27 feet cubed. What dimensions yield the minimum surface area round to the nearest tenth? So we've got an open-top, square-base, rectangular metal tank. And I'm going to try and draw that sucker because we need to see what we're dealing with. Alright, this is not too shabby here. Maybe not quite super awesome, but not bad. Okay, I've got a square base, so I'm going to go ahead and label that as x and x because they're both the exact same length, and they tell us, hey, we got a square base. I'm going to go ahead and label my height y. So that gives me my two variables, x and y. And we want to find the dimensions that yield up the minimum surface area. So the surface area equation is the one we're going to take the derivative of. But when I look at surface area, I'm going to have, like if you look at this one side right here, this one side, the area of this one side right here is x times y. And there's 4 of those. So surface area equation is going to be 4xy plus the bottom part of our square, which is x squared. The surface area down there is x squared. So here's my surface area. I'm told that my volume is going to be x times y, which is the same thing as x squared y, and they tell us, hey, that's going to be 27 feet cubed. So my volume is going to be 27. If I'm going to maximize the surface area, I need to take the derivative of the surface area equation, this guy right here. But I've got 2 different variables running through there. It just won't work out that way. So what I'm going to do is I'm going to come over here to the volume equation. I'm going to divide both sides by x squared so that y equals 27 over x squared. We could also think of this as 27x to the negative 2 if we want. So I don't know how we're going to want to do that, but it's going to have to be, you know, one of these ways will work for us. I just don't know which one yet. We'll find out. So what I'm going to do is everywhere I see a y, I'm going to plug in that 27x to the negative 2, or 27 over x squared. So here's my y right here. That's the same thing as this y right here. What does that mean? It means the surface area is equal to 4 times x times y plus x squared. So there's the surface area equation right there. This is the one we're going to take the derivative of. But how it looks right now, it's not super friendly the way that it's written. So notice that I've got an x in the numerator and one of those x's in the denominator, and 4 times 27, that's 108. So I'm going to have 108 x to the negative 1 plus x squared. This is the equation I'm going to take the derivative of. Now, it is 108 over x, but I don't want to take the derivative of that. It's a little bit more work, in my opinion, but you know, if you're more comfortable that way, that's fine. So the derivative then is going to be negative 108 x to the negative 2 plus 2x. Okay? And so what we're going to do is we're going to actually set this part equal to 0. Negative 108 x to the negative 2 plus 2x equals 0. So I'm going to go ahead and move the 2x over. And now watch, the hand is quicker than the eye here. Negative 1 over 8 over x squared equals 2x, negative 2x. And what we can do is cross multiply right here. So I can multiply both sides by x squared, negative x squared. And let me find my color. Where'd it go? So what I end up with is 108 equals 2x cubed. And when you divide 108 by 2, you get 54. And we're just going to take the cube root of both sides. And so when I do that, that gets me x on the right. And then the cube root of 54, that's not one that I kind of carry around in my back pocket. Plus, I really am interested in dimensions here. So I just punch that into my calculator and I get 3.78 feet. So that means my dimensions here are 3.78, 3.78, and then the y value, what's y? Well, it's right here. That's what y is. So when you punch that into your calculator, you should get, let me double check, you should get 1.9. So there you go. The dimensions and all of these, of course, are in feet. There you go. I like it. Okay, in this problem, we want to find the number of units that need to be produced in order to yield a maximum profit. And one cool thing about max profit is if we have a cost and a revenue, max profit's really easy to find. You take marginal revenue, which is R prime, and you set it equal to marginal cost, which is X prime, and that gives you maximum profit. We love these problems. We should have a whole test of these, okay? And so when I'm working this out, I just need to know what R prime is. So R prime of X is 60 minus X squared. Let me double check that. I think that's right. Yep. Or 60 minus X, not X squared. Yikes. And then C prime of X, C prime of X is just 9. So it gets even easier because then all we're going to do is we're going to set 60 minus X equal to 9. Go ahead and subtract 60 from both sides. And X equals 51 units. That's the number of units that will maximize profit. And that's all there is to this particular question. Okay, here's our first linearization problem on the review, and linearization is just simply a pattern, and it looks like this. L of X, linearization of X, is equal to f of some special point, whatever we're told it is, f of a, plus the derivative at a times x minus a. That's your linearization formula. It's just a formula, so we need to find some specific things. Number one, we need to find f of a. So here's f of x. F of a just simply means negative 8. So that's going to be 7 times negative 8 minus 2, and that's negative 58. We also need the derivative of that. So the f prime of x is going to be 7x. So guess what f prime of 8 is going to be? You put an 8 everywhere there's an x, 7. Okay? Not too challenging so far. So then we just plug everything back into this formula. So f of 8, okay, f of 8, negative 8, that's negative 58, plus f prime of that times x minus 8. So it looks like this. And if we're going to find the linearization close to here, then we just work this guy out, and it's going to give us an equation, which is going to be L of x. So negative 58 plus 7x plus 56, combine all the loose parts together there, and the linearization of this particular guy is going to be 7x minus 2. That's it. That's all there is to it. And what are we talking about? That means on the curve 7x minus 2 at the point negative 8, when x is negative 8, what shape does my tangent line look like? And it looks like 7x minus 2. And if you think about it, that's the kind of line we're dealing with. Okay? Kind of makes sense. So there you go, linearization. We're going to do a few of these now, and hopefully by the time we're done with these, you'll be experts. Okay, on 5, we want to use linearization to approximate this guy's an answer. Sorry about the extra lines here. So what does that look like? Well, I just follow this pattern. It tells me what pattern to follow. And there's not really much calculus-y stuff going on here. I just got to break my problem up into this. So basically what I have is 1 plus 0.000, whoops, one more 0, 0.06 to the 50th power. So if I follow this rule right here, then this is approximately, not exactly, approximately equal to 1 plus 0.0006 times 50. Okay, so work that out. What is that? That's 1 plus 300ths, 0.03, which is 1 plus 3/100, which is 103 over 100. Now, the reason I did it all the way down to here is because it asked for my answer in a fraction. So when they give you this linearization pattern for a little binomial, follow the pattern. It makes life just so much easier to work through. And the pattern's not hard. You just do it. You do, in this case, do exactly what it says. All right, again, we want to find an approximation for values of x near 0, and they give us this function. So I'm just going to rewrite this function just real quick. I'm not going to do anything earth-shaking to it, but this is the same thing as that. 3 times 1 minus x to the -1 power. Hey, guess what? That's a binomial to a power, so we can use our cool little rule, which says that 1 plus x to the k is approximate to 1 plus kx. Look, here's my 1 and my x. So what does this look like? Well, if I'm going to find an approximation for this function, I'm just going to follow my rules. 3 times 1, and remember this is plus negative x here. Okay? So that's approximately equal to 3 times 1 plus k times x and so my approximate linearization for this particular guy is just going to be 3 plus 3x. And really, that's all there is to it. We're just trying to match up to this pattern right here that they gave us, and they told us that it's true. So we're just trying to squeeze into that guy any way that we can, and just following some basic simple rules here, we're able to do so. All right, this is a really fun one. What we're going to do is we're going to approximate the square root of 103 using the linearization process. I think this is really cool because now it gives us sort of a way to kind of find a square root of a number without necessarily being totally strapped to our calculator. At least it narrows it down for us. So let's just refresh. A linearization is f of a minus, no, not minus, plus f prime of a times x minus a. That's your linearization process. So the function we're working with here is a square root function, okay? And we're told that x equals 103. So what we need to do is we need to pick like a square root that we know that's really fairly close to 103. And there's a couple of choices here. There's 121 and 100. The square root of 100 is 10. The square root of 121 is 11. So we know both of those. But 100 is closer to 103, so that's the one we're going to pick. That is going to be our A. So what I'm going to do is I'm going to go f of A, f of 100, well the square root of 100 is 10. I need the derivative of the square root. Which is the same thing as 1 over 2 square roots of x. Okay? And I need this also solved out at 100. So that's going to be 1 over 2 times 10 because the square root of 10, or square root of 100 is 10. So that's 1 over 20. Okay? So now I have all the pieces to plug into my linearization formula. So here we go. I just take my f of a, 10, plus f prime of a, that's that guy right there, times x minus a. X we said was 103. A is 100. And so I end up with 10 plus 3 over 20. And we could do all kinds of things with this. Like we could add fractions. We could convert to decimal. I mean, lots of options here. It's like not an impossible problem now all of a sudden. Go ahead and if you just plug this into your calculator though, just the 10 plus 3 over 20 part, not the actual square root of 103 part, but 10 plus 3 over 20, you're going to see that you're going to get 10.15. And ask yourself, does that make sense? You know, is that something that would be a good approximation for the square root of 103? Well, if the square root of 100 is 10, and we're just a little bit past that, 10.5 could probably work. So there you go. That's using the linearization formula to find a square root of a number. All right, Newton's method. Have a calculator handy for Newton's method, and I'll, if I can remember, I'll add to the screen here what I do whenever I use Newton's method on my calculator so that you can see it. You can do this with both the 84 and the Inspire, this little trick. But basically it's just like a division algorithm. You're just going to take the same process and go through and through and through it. When you get to the end and you get a number, that's the number you're going to start with for the next time through the process. So let's just real quick have some sort of thing of what Newton's looks like, and it looks like this, where the next term, n plus 1, all right, is equal to our original term minus the function at that term divided by the derivative at that term. And basically, this is a really cool way to find zeros. And you just need to be in the ballpark of the zero that you're interested in. And once you're in the ballpark, after a few times through Newton's method, it lines everything up exactly perfect. And you can get a zero to like 7 or 8 decimal places, which for us is really pretty good. A lot of times when we are trying to find a zero, we're only interested in maybe 3 or 4. So the problem they give us here is 2x to the 4th minus 3x squared minus 7x plus 1. We're going to need a derivative in there. So here's your derivative. And then what we're going to do is we have to pick a starting zero. And there's 2 zeros on this particular problem. And the first zero looks like it's close to 0. The second zero, and you'll need to graph this to looks like it's close to 2. Okay? So what I need is, I need the function at 0, which is 1. I need the derivative at 0, which is negative 7. And so here's what I punch into my calculator. x1 is equal to 0 minus 1 divided by negative 7. And I did that on my calculator and I got 0.142857. All right, now for the second derivative, or the second term through Newton, we're going to take this number 142,857 minus, and then we're going to do the function of that. And what you want to do is you want to keep that original number in the function because you want as many decimal places as you can get. Divided by the derivative of that. And when I punched that into my calculator, I got 0.135148. And then I'm going to come down here for the third guy, and we want it to be accurate to 7 decimal places. So we want to be able to line these decimal places up so that they're the exact same. All right. So the third guy, 0.135148 minus the function of that divided by the derivative at that. And this gets me 0.13512698. And I'm going to do that same process again. And I'm kind of running out of room, so I'm not going to write out exactly what it is. But you see the pattern here. And so when I work this pattern with 0.1351268, when I get done, I end up with 0.135126985. And notice how these guys match all the way to here. Notice how they match all the way to there. So that's when we know that we've gone far enough, when we can line up all those decimal places together. So I'm going to do the same exact steps over here on part 2. So I need to know f of 2 and I need to know f prime of 2. And once I've got those things, I use these steps and I punch everything into my calculator, and on my calculator kind of grind through some stuff. So I need to know what these two guys are, and what I got. I punched all this into my calculator. You can too, and I'll show it. But for x1, I got 1.8444. For x2, I got 1.8123. 9368. For x3, I got 1.8111. 03994. For x4, I got 1.1811. 0195. 2. And then when I did the second one, or the fifth one, I got the same thing. It changed back here, but I'm not worried about that. I just want to line up those. So I'll have a calculator up that shows you how to do this also. It's really easy to do. It's just an algorithm. But that's how Newton's method works. It helps you find zeros of graphs. And you don't necessarily need to have a graphing calculator to do it, although a calculator sure came in handy.